Welcome to this video. In this video we're going to review October Progress Test E, and we'll look at Part B, the multiple choice. So our first question in the multiple choice section is, what is the best oxidizing agent? And the first thing you have to ask yourself is, what is an oxidizing agent? And so we know that an oxidizing agent causes oxidation, and we can remember the mnemonic oil rig. Oxidation is loss. So if we're going to cause loss, we have to do that by taking. So an oxidizing agent is an electron acceptor. It's going to pick up electrons, which immediately means we can cancel out these two because they can't accept any more electrons. They've already accepted to achieve a full shell. So F- and I- are not oxidizing agents. So we're left with the halogens, fluorine F2 and iodine I2. And which one of those is best at accepting? So think about their size. Think about what it is that attracts electrons. So it's going to be the protons in the nucleus that attract electrons. So whichever one has the greatest attraction from the protons in the nucleus will be the best oxidizing agent. And since fluorine is smaller with less shells and less shielding, then the power of the protons in the nucleus to attract electrons is going to be more, and therefore fluorine is going to be the best oxidizing agent. And our second question in the multiple choice section asks us to think about molecular energies of a gas, the distribution curve. So this is the Maxwell-Boltzmann distribution curve. See if you can think what that looks like. So on our axes, which we've got number of particles or number of molecules up the side and energy along the bottom, we know that the Maxwell-Boltzmann distribution is skewed to the left and then becomes asymptotic, follows the x-axis without touching it. So is that symmetrical about the maximum? Well, the maximum point is here. Is that symmetrical? No. It goes up much faster than it comes down. It says there are always some molecules with zero energy, which would mean it would have to start up the y-axis somewhere. Well, it starts at the origin, so that's not true either. The position of the maximum is not dependent on temperature. Well, that's not true either, because if I were to heat this up, the peak would move to the right and lower down, and then the curve would stay above the original from that point onwards. So the position of the maximum is dependent on temperature, which means the last one should be right, but we can double check it. Mean is where we add up all the different energy values and we divide by how many there are. The mean average would be somewhere around here. It would not be where the most probable, which is the most frequently occurring, which is this point here, the peak. So our mean is greater than the most probable. So D is the correct answer. Our next question looks at ionization energy, and ionization energy relates to the amount of energy to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. So we're looking at this process. We need to think about position in the periodic table. So we've got hydrogen in the kind of floating in the middle, and then we have got lithium at the top of group 1, and we have got neon at the other end of that period and helium up here just above neon. So we've got like a periodic table where hydrogen floats on its own, and this is the top of the S block here, and this is up here at the top of the P block, which kind of carries on like across like that, and then they connect in the middle, don't they? So from lithium to neon, there would be a general increase in first ionization energy because we've got the same shell, similar shielding but more protons. But from helium to neon, there would be a decrease because we've got more shells and more shielding. So from hydrogen to helium, there would also have been an increase because they're in the same period, which means that helium is going to be at the top of that because the arrows point from helium. So helium, we're going to increase to helium and then decrease down to neon. Helium is going to be the one with the greatest first ionization energy. So our next question asks us to identify the number of chiral carbons. Now we have to remember that is an asymmetric carbon, 4 different groups. So let's go around every carbon and see if there are 4 different groups attached. I'm going to start here. Whenever there's a double bond, there's not 4 different groups. So where there's a double bond, there's only 3 things. So again, there's only 3 things attached here. 1, 2, 3, And we've got the fourth bond is to a hydrogen, so there's 3 different groups attached. There'd only be 3 things attached here, 1, 2, 3, that's all of those. Here there's going to be 4 bonds on this C, but 2 of them are going to be H's. So I'm not going to write all these H's from now on, but everywhere that we've got a point on this ring that's only got 2 sticks coming out of it, there would be 2 hydrogens, and none of these will be chiral because they've got 2 things the same. Now every other place where there are 1, 2, 3 sticks coming out of this carbon, then the 4th stick would be a hydrogen. That's 4 different things. There's 4 different things. There's 4 different things. There's another one with 4 different things. Here, the methyl group is the 4th thing. There's 4 different things. Here, we've got 1, 2, 3 sticks and a 4th different thing coming out. So, and then this one here, we can just double check, but this would have 3 H's on it. So there's 1, 2, 3, 4, 5, 6 circles. The correct answer is B. Okay, so our next question is going to take a little bit more work. We've got to think about how sodium hydroxide will react with a diprotic acid. Now it's given us the formula of the diprotic acid as that, and we should know the formula of sodium hydroxide, and even if we didn't, it's below in the question. And then you have to say to yourself, acid and alkali react to make salt and water. And we need to work out the formula of the salt. Now given that the formula of the acid is H2A, the salt must contain 2 hydrogen ions, the acid must contain 2 hydrogen ions, and the anion A must be 2- to balance the 2 H pluses. So we know that the anion is A2-, and we know that a sodium ion is Na+, and we know that we replace the hydrogen ions of an acid with the metal ions when we form salts. So we're going to replace and come up with our formula of our salt. So to balance the equation, we put a 2 there and a 2 over here in front of water, and we've now got the ratio is 1 acid to 2 sodium hydroxides, which is going to be important. So the next thing to do is turn this mass and MR into a number of moles of diprotic acid. And moles is mass divided by MR. And if we do that calculation on our calculator, we're going to be getting, so you type that in your calculator, do it in my head, is it 0.05? And now we're going to use that ratio to find the number of moles of sodium hydroxide. So the number of moles of sodium hydroxide is 2 times that, because it's a 1:2 ratio, so 0.10. And the next step then is to go to each one of these and work out using moles that are very clever, volume times concentration, remembering that because concentration is in moles per decimetre cubed, volume must be converted. So I convert by doing times 10 to the minus 3, you might do divide by 1,000, same thing. You work this out, you can work out the number of moles in each of these bits, and you can repeat this calculation method on each of these numbers to get the moles. And when you do that, you'll find that it's C that gives you the right number of moles. So our next question is looking at electron configuration. So you're going to need to go to your periodic table and find carbon. Carbon's number 6. And if you find it, you'll find that its electron configuration is 1s2, 2s2, 2p2. So we can immediately rule out A and B because they've only got 2s1. I'm just going to scroll down a little bit. And then we're looking at C and D. Now both C and D have got the right number of electrons in each subshell, 1s2, 2s2 and 2p2. So both of these are correct, but one of them is obviously incorrect. We need to figure out why. And this is where we need to remember that extra rule about electron configurations, that electrons will go unpaired if possible. So they'll fill up every orbital. Remember, these boxes represent orbitals. We're going to fill up every orbital first before we pair up. So these have paired up too early. So this is wrong. So that makes D the correct answer. And our next question is all about equilibria. And if we want to increase the concentration of SO3, given that SO3 is over here, we want to shift the equilibrium to the right. So we're going to go through each of these and see, according to Le Chatelier's principle, whether it's going to shift the equilibrium to the right or to the left. So a higher concentration of O2. O2 is a reactant. According to Le Chatelier's principle, if we increase the concentration of a reactant, equilibrium must shift to the product side in order to reduce it, so it's going to shift it right, which is what we want. But let's just double check that we haven't made a mistake by checking each of these other three. So if we increase the temperature, according to Le Chatelier's principle, we need to move in the direction which reduces the temperature, which is the endothermic direction. Now, given that this reaction is minus exo, moving in the endo will be moving backwards, and that's not what we want. According to Le Chatelier's principle, if we lower the pressure, we need to shift to the side with the most moles, because more moles have higher pressure. And here we've got 3 moles on the left and 2 moles on the right. So we would shift left to the side of higher pressure, which is not what we want. And the last thing on here is if we were to use a catalyst, according to Le Chatelier's principle, we can't really deal with this one, can we? Because catalysts have no effect on yield. What they do is they speed up both the forward and the backward reaction by the same amount, and so there is no effect. So that's not going to increase the yield either. So we were right, it is A. Right, our next question is an empirical formula question. So remember, for an empirical formula question, the best thing to do is to set it up with mass at the top. Now, we had 4 grams of molybdenum and 5 grams of an oxide, which means that we have to do 5 minus 4 to get the grams of oxygen, because if it's 5 grams of the whole thing and 4 grams of molybdenum, then it's 1 gram of oxygen. And the little rhyme, the little haiku goes, convert mass to mole. To do that, we divide by the AR. So we need to go to our periodic table. We need to find molybdenum. It's not that easy to find, but if you find it, you find that it's in the transition metals there. It's got an AR of 96. Oxygen is much easier to find. We're used to oxygen. So convert mass to moles. So we convert mass to moles by dividing by AR. So we're going to divide on our calculator 4 by 96 and 1 by 16. And if you've managed that, you should have got these two numbers. So I've converted mass to mole, and then we divide by the smallest. So we want to get that simplest ratio. So we're going to divide by the smallest. We're going to divide them both by this. If we divide by 0.0417, this one becomes a 1, and this becomes a 1.5. So the haiku goes, convert mass to mole, divide it by the smallest, multiply till whole. Now these aren't whole numbers, so I'm going to times by 2. I'm going to multiply, because if I times by 2, I'm going to get whole numbers. I've got 2 molybdenums and 3 oxygens, so C is my correct answer. So my next question is an enthalpy profile diagram question. So I'm looking at this before I even start, and I'm thinking to myself, this is an exothermic reaction, because the products are lower in energy than the reactants. Energy is given out. I'm looking at the forward reaction here with an activation energy of 150, and the enthalpy change is minus 120. So the first one says the activation energy of the forward reaction is 120. Well, no, the activation of the forward reaction is this up arrow here. It would be 150. The activation energy of the reverse would start at this products line and go all the way up to the peak. So you would add up the value of these two lines. So is 150 add 120, 270? Well, it is. And so B looks like it's the right answer, but let's just check out C and D. The enthalpy change of the forward reaction is from the reactants to the product, so it's minus 120, not minus 30. So that one's wrong. And the reverse is exo. Well, no, the reverse is very definitely endo. The forward is exo, so the reverse is endo. So it was B. So our next question deals with alcohols. My first job would be to draw out this structure to see if I can manage it. So I've got CH3 attached to a C with a H. I've got 2 of those. So I'm going to put one up here and one at the side. Then I've got a C with an O, which must be a double bond O, and then a CH3. Now if I look at this structure, this is a ketone. So what could be oxidised to form a ketone? Well, when we oxidise and make this, we don't affect these other bits at the other side, so I'm just going to copy them. So the oxidation doesn't affect these parts at either side. It just affects the functional group carbon. And it does that by removing a carbon-hydrogen bond in order to make that double bond. And so it must have come from this secondary alcohol. We removed this CH bond down here in order to make a double bond O. This was our oxidation of a secondary alcohol to a ketone. So now we need to name this. So if we start nearest to the functional group, which is the alcohol, we got 1, 2, 3, 4, bute. All the C's are joined with single bonds, so butan. Number 2 has got an ol, so butan-2-ol. And number 3 has got a methyl, so 3-methyl-butan-2-ol. So the correct answer is D. Now what we've got butane reacts with chlorine. So butane, C4H10, reacts with chlorine. In the presence of ultraviolet radiation, we do a free radical substitution and swap one of the H's for a Cl. This would be our overall equation. So propagation is where a radical and a molecule react to make a radical and a molecule. This first step, A, is an initiation where the molecule is broken down into radicals, so that's an initiation. And this B is where two radicals come together to make a molecule. Oops, I shouldn't have ticked that, should I? That's a termination step, and therefore that's not what we want, that's not propagation. Now, here we do have a molecule plus a radical makes a molecule plus a radical, but it wouldn't be in this mechanism, and also this could not happen, this product, because if this chlorine radical here attacked this molecule, what you would end up with is not this, it would pull off a hydrogen, that's what it always does to make a radical, and HCl. So when a chlorine radical attacks a hydrocarbon containing thing, it pulls off a hydrogen to make HCl. So this is not the product, so this is just not a possible thing. And then here, when that chlorine radical, this is making what we thought, so it is going to be D. So now we've got a question about boiling point. Boiling point is all about structure and bonding. And remember that there are 4 types of structure. We've got giant metallic, giant ionic, macromolecular, and simple molecular. And if they're giant metallic, giant ionic, or macromolecular, they're going to have a high boiling point because we've got some bonds to break. If they're simple molecular, we're going to be looking at our 3 types of intermolecular forces. We've got van der Waals, permanent dipole, and hydrogen bonds. And we know that of those, hydrogen bonds are the strongest. Now if we look at these, they're not metals, they don't contain a metal, so they're not ionic, and they're not one of our 4 macromolecules, silicon, diamond, graphite, or silicon dioxide. So they're simple molecules, and we then need to decide which of these intermolecular forces they have. Now when you've got Br, which is more electronegative than C, then we're going to have PD, permanent dipole forces. This one with the F in is to trick you, to make you think it's got hydrogen bonds, because remember that hydrogen bonds is when they've got N, O or F, but they've got to be joined to a H in the molecule. Now this F is joined to the C. If you drew it out, it's joined to the C. So if it's joined to the C, all it's got is a dipole force. Here, again, trying to trick you by making you think they're connected, but this is an aldehyde, you have to know your chemistry. So this is again permanent dipole, and here in this last one, now the H is attached to the O. So we've got hydrogen bonds between the molecules, so D will have the highest boiling point because hydrogen bonds are stronger than PD. This is another one where we're going to need to use our data sheet. So we need to grab hold of that data sheet and we need to identify some of these. Remember that 1500 and below we ignore because that's the fingerprint region. So we want to try and work out what this peak is, what this peak is, and what this peak is. So we go to our data sheet. We've got one at around about 1700. This is a C double bond O. Then we've got something just below, about 2800 to 3000-ish. So like sharp, jagged one. This is a CH. And then we've got another peak at about 3200-ish to 3000 700-ish, and if you go to your data sheet you'll see that that is an OH, but not any OH, it's an OH alcohol, not an OH acid. Now if this was an acid, just temporarily draw on this, then the acid peak sort of goes from around about 3000 and it extends all the way to 2500 and looks much bigger, much wider. That would be our OH in acid peak. And this is an OH in alcohol. So that means it's not ethanoic acid because it doesn't have the OH acid peak. Propan-1-ol wouldn't have a C double bond O peak. This would have a CC, and CC comes a little bit lower down, 16, so the CC would be like here and usually a bit smaller, and so it's not that. Also we'd need that C double bond O. So we're left with the 4-hydroxybutanone, and because we're calling it butanone, which is this, we've actually had to call that the alcohol a hydroxy, so it's B. What we've got here is a rice question. So set out your equation again, NH3 in equilibrium with a half an N2, because we've got moles of gas in the equilibrium mixture. Write down rice. And the ratio is 1 to a half to 1.5. The initial amounts, 1 mole of ammonia, 1 mole of ammonia, no products at the start. When 50% had dissociated, so we've lost half of it, so we've got half left. Now, it's the change and the ratio line that need to be in the same proportions. So if this is minus 0.5, these two are going to be plus something because they're products, but the amount of nitrogen is half the amount of ammonia, so it's plus 0.25, so nothing add 0.25 is 0.25. And this one is 1.5 times the normal amount, the 1 amount, so 1.5 times that is 0.75. And now if we add up the total number of moles, we would get 1.5, which is A. So that is all of our multiple choice questions on this test E. And hopefully this has helped you understand where you went wrong in your test.